we will use UDU pretty much every single day. This method right here, it's a little bit messier. We're not going to use it every single day, but we do need to know it. It does pop up frequently left where we do need to know it. Colleges don't really call this XDX. This is just my name for it, just so I can have something to differentiate it from our UDU technique. But the UDU is, what the colleges call that method there. This is a little bit messier. Typically on an XDX problem, all right, I would jot these steps down and we're gonna follow these steps. If you listen and do these problems the way I'm asking you to do those, I'm gonna try and give you some tips here that makes the problems a little bit smoother. If you go off on your own, start doing some stuff that I'm not telling you to do, you get extra fractions in there, extra fractional exponents in there, and it just gets a little bit messier right there. Typically, the only time I do an XDX, it works in a couple situations, but really the only time I go straight to it is if I have radicals in the problem and a UDU is not working. Okay, so notice that if I had an x squared minus 4 inside that radical, that's a UDU, because if I let the u equal the x squared minus 4, the du is equal to a 2x. I get the x to match up, balance the 2 with the 1/2. But see, if I let the u equal the x minus 4, the du is equal to 1, I'm not getting that x to match up. All right, so a lot of times you'll see if you have like a higher degree out here instead of on the inside, or if you have the same degree on the net, then the UDU isn't going to work out for us. Okay, so if I have radicals in the problem and a UDU isn't working, and it's not like a normal problem there, then I'm just going to go to the XDX. So a little bit different. Here, I think we're going to need the steps. UDU, you probably didn't need the steps too much there, but we're going to choose U. Now, when I choose U on an XDX problem, it will work if you let it equal the inside part, but if you let it equal just the inside part, I'm telling you, you're going to have more fractions and fractional exponents on the inside of this integral, and I think the problem is always going to be worse when you do that. So whenever I choose U on an XDX problem, I almost always let the U equal the entire radical part of the problem. And what that happens is, just my experience of working these out, is you're going to get nicer exponents and stuff in there and a little bit less fractions and stuff that we got to deal with, right? So choose U on an XDX problem, let it equal the whole radical, just give that a shot, let that work out for you, right? And then this time we're not taking the derivative right away, we're going to solve it for x. So I'm going to cube both sides, and I'm going to move the 4 over. And you got to just follow those steps. So we choose U, let it equal the whole radical part, solve it for x, get the x equal something, and now we're going to take the derivative. Let's find the dx. So I'll take the derivative of this, tag on the du, and then the next thing we're going to do item for item substitution. There is no balancing with reciprocals on an XDX method there. So you're going to plug in everything. So everything is going to get substituted, and we're going to replace all the x's in terms of u. So I'm going to rewrite this integral. The x is equal to the u cubed plus 4. And the nice thing is this whole entire radical is the u part. So that whole radical is u. And then you also got to remember to substitute for the dx. The dx is equivalent to 3u squared du. That's a pretty significant deduction if you forget that. Sometimes it makes the problem too easy and I can't grade you on the harder part that it was supposed to be on. And then sometimes if you don't remember that, then it makes the integral sometimes a little bit impossible or more or worse, and you can't actually integrate it with this chapter's methods right here. So you got to remember to substitute for that dx. I remember when I was in college working these out, sometimes I would forget that. And I'm like, oh crap, and I would just kick myself because I'd have to go back and just restart it from that step there, and I'd redo a bunch of steps right there. So remember to substitute for the dx. So again, everything gets accounted for here, item for item substitution. There is no balancing anything there. Everything gets accounted for. And now right here, we have nothing but u's. And at this point, sometimes you got to do a little bit of legwork. Like if you have this binomial squared, you're going to need to multiply that out. All right, so we're going to need to just kind of distribute stuff here. Now, this is your integral. This 3 is part of your problem. So I'm allowed to pull the number out in front. And then you have a u times u squared. So u times u squared is really a u cubed that I'm going to take and distribute through the parentheses. And we're going to add up the exponents there. Let's be careful with our algebra. And so notice what I have right here. This is a very simple integral. If you let u equal the inside part, you're going to have fractional exponents right there most of the time there, okay? So sometimes it works out all right, but then you're just making that problem a little bit worse for yourself there. So that's why I let you go the whole radical part, because then I get nicer things right here. All right, so I chose the u, solve for x, find dx, item for item substitution. Once you get the hang of these steps, that's really not your issue right there. Just sometimes right here, sometimes you got to multiply stuff out. Sometimes you got to have to deal with some fractions and stuff there, and it gets a little messy. But typically you get something relatively simple to integrate. So the next thing we're going to do is integrate this thing. So that 3 carries down, and then we're just going to go u to the 7th over 7. We're going to get 4u to the 4th over 4. So the 4s are going to cancel. So it's going to make that u to the 4th. Now, technically, I'm done with the calculus. I'm done integrating. Now, when you're checking answers in the back of the book, we're not getting the first answer. You're giving me the second answer, okay? And if you follow what I do right here, you're going to automatically get that second answer. There's not going to be any confusion, okay? So let's practice these steps. You don't, on an indefinite integral, you don't want to plug your x's back in too soon, because then you're going to have something to the 7th third, something to the 4th thirds, and then you're going to have to do those tougher factoring problems right there. And we don't need to do that if you follow these steps I'm going to give you. So I've got 2 examples here. If it's an indefinite integral, no numbers attached, what this one is, what I want you to do before you plug your x's back in is get a common denominator, one single fraction, and a GCF first, and then plug those x's back in. If we do that, I'm just trying to make this easier for you. So if you follow this, hopefully it goes a little smoother, but we're still going to do factoring. But see, now we get to do factoring with easier exponents, easier GCFs, and it's just go a little bit quicker, and that'll save us a little bit of time, and you're not making things too complicated there. So again, indefinite integral, after you integrate it, right here, you're following this green stuff here, common denominator, one single fraction, which means I'm going to go here. I'm going to put like a 7 there and a 7 there. There's my common denominator. I'm just going to stick that 3 on the top there. And so there's my common denominator. There's my one single fraction. I really don't need to put that plus c into the very end right there, so I don't need to worry about it too much. But the next thing we're going to do is a GCF. Don't plug your x's back in yet. Do a GCF, because look how simple this GCF is. You just pull out the 3u to the 4th, got u to the 3rd plus 7. All right, so I did my common denominator, one single fraction. Now I'm going to do the GCF. Now, I'm sorry, I just did the GCF with those nice, easy exponents. And now we're going to plug the x's back in. So when I go plug my x's back in, I realize that this is really x minus 4 to the 1/3 power. So I'm going to take that and stick that in right there for the u. Now, when you have something raised to the 1/3 and then you raise it to the 4th, Algebra 1 days tells us that we're going to multiply those exponents together. So I'm going to have that as x minus 4 to the 4/3. And here's what's nice. Even if I can do some of these steps up here in my head, I always write those down, because when I get to the end of the problem, they're always right there in front of my face, and I don't have to think as much there. So when I see a u cubed, right there, u cubed is equivalent to x minus 4. So that u cubed is equal to x minus 4. So if I plug that in place for the u cubed, I get x minus 4 plus that 7. That will give us x plus 3. And then you have it all over 7. You have your plus c, and then you're done. So that concept, I know that just seems like a lengthy process right there. You're just going to need to practice a few of those and get that process down. And again, this should be the second answer in the back of the book that we need to match. I need to get that answer right there. Don't plug your x's back in too soon. Leave it to the 7/3 and to the 4/3. We're going to need to get this answer right here. So again, indefinite integral, all it is, very simple. Common denominator, GCF first, then plug your x's back in, and we're always going to have that smooth looking answer there. If you have a definite integral, I'm going to share with you that in 1 second here. Actually, yeah, let's just do this one next. All right, I got 2 more examples here for you there. Now, notice that this is the same exact thing as this, okay? So I'm not going to do everything from scratch. I would do everything exactly the same until I got to this part right here, okay? So I would choose the u equals the radical, solve for the x, find the dx, item for item substitution, and integrate it. And these are separate steps here. If it's a definite integral, you don't have to do all that extra work, okay? You could stop and plug in your numbers right away. So let's review that. So what I'm going to do here is I'm going to integrate it. So after I integrate it, I got to this part. So I'm going to start right there at 3 u to the 7th over 7 plus u to the 4th. So I'll do everything like normal until I got the right here. Then if I have numbers attached, that's a sigh of relief, because I don't have to get the one single fraction, don't have to do a GCF. I'm going to stop right here, and I'm going to do my fundamental theorem of calculus, and I'm going to plug in numbers. You just got to be careful. I can't plug in the 12 and the 31, because the 12 and the 31, that's a dx problem. Those are x's. And now I have u's in the problem there. So if you plug your x's back in, then you use the 12 and the 31. But I don't want to have to plug x minus 4 to the 1/3 in for those x's and deal with all that. It's simpler, it's quicker if we just stop right here, switch our x's to u's. So the way you're going to do that, this was your initial substitution step, right? Going back to that first step on that problem, this is what you use. Those are x's. So you're going to take those x values, plug those in place for x, and then get your new u value right there. So take the top number, plug that in, 31 minus 4, that's going to be the cube root of 27, which is equal to 3. And then take your bottom number, plug it in, 12 minus 4 is 8, cube root of 8, that's equal to 2. It doesn't matter if those numbers are like that ends up as a 2 on the top and a 3 on the bottom. It's not like least to greatest like it normally is. Don't worry about that. Just top number, plug it in, that's your new top number. Bottom number, plug it in, that's your new bottom number. Whatever that is, that's what that says. Top stays with the top, bottom stays with the bottom. And now all you have to do, since you switch your x's to u's, that's what I'm talking about here. We stopped after we integrated, switch those x's to u's, and now I simply just have to plug in the numbers and get an answer. So remember your fundamental theorem of calculus is you plug in the top number real quick. Okay, marker keeps stopping on me. All right, so you plug in the top number like that, and then you go minus, then you plug in the bottom number. All right, and then just get some numbers for that. I'm just going to tell you what that stuff is real quick. Be a minus 128 over 7 minus 16, and then you got the 3. All right, and then it's just arithmetic after that to get this final answer there. So remember, on the definite integrals, you got to give me the number. There is no plus C on the definite integral, so just plug in the numbers. Be careful with your arithmetic there, and just plug that stuff into the calculator, get that number answer. All right, now, this last example, I already got most of it worked out for you. Not everything in this section, in this homework assignment, will be an x dx. There is quite a bit of u du in there, so always try u du first. Not going to go to an x dx thing. If you try an x dx on this, it may very well work, but you're going to do like 18 steps when you should just be doing like 2 or 3 steps there. So always try u du first. And if you have radicals in the problem and you know what u du isn't working, so because it's not matching up right, then you're going to do an x dx approach there, right? But notice if I let the u equal the inside like normal, the du is equal to that, and I actually get that x dx to match up. So that's a u du problem. Balance the 2 with the negative 1/2. I got the square root of u, integrate that, u to the 3/2 divided by 3/2. I just want to share with you on this one, since I showed you how to switch the x's to u's on this problem. On a u du problem, you have an option. There's 2 ways that you could do a definite integral on a u du problem. You don't have to plug your x's back in. If you wanted to, you can stop right here and you can plug in numbers, but you just can't plug in those numbers because those numbers are x's. So you would have to use your initial substitution step always to switch your x's to u. So if you take the top number and plug it in place for x, so if I take that 1, plug in for x, I get 1 minus 1, that gives me 0. And if I take the bottom number plugged in for x, I get 1 minus 0, which gives me 1. Now, the fact that those flip like that was a pure coincidence. Notice that here, most of the time you get brand new numbers right there, so they're not just going to flip those numbers there. But see, those are your u's now, and now you could do your fundamental theorem of calculus. So I'm always going to take that negative 1/3. If it's a constant, I always just like to pull it out in front, and then you're going to go 0 to the 3/2 is 0, minus 1 to the 3/2 is 1. That's going to be negative 1 times negative 1/3, gives us a positive 1/3 for the answer right there. So think about on a harder problem where your u might be like a trig equation or something, a trig function or a crazy something else, then a lot of times that u is a little bit too involved where you don't want to plug your x's back in. But on this one, if I wanted to, once I got to this part right here, a negative 1/3 u to the 3/2, if you don't want to switch your x's to u's, you can use the original numbers. Just to use the original numbers, you got to plug your x's back into the problem. All right, so it'll be like that. And then you'd stop and integrate. But now since you have x's in your problem, then you're going to use the original numbers, the 0 and the 1. All right, and then so the negative 1/3 is still out there. And then you're going to plug in the 1. So 1 minus 1 is 0. 0 to the 3/2 is going to be 0. And then you go minus, take the 0 plugged in. 1 minus 0 is 1. 1 to the 3/2 is 1. And you're still going to get a 1/3 right there. So on a u du problem, I don't care which way you use it. You either plug the x's back in and use the original numbers, or you stop and you switch your X's to U's and you plug in those U's right there. Don't mix them, all right? Sometimes I have students, they'll plug the X's back in and then they'll switch them to U's and then they're plugging in these numbers here when they should just be using the original. So if you plug the X's back in, use the original numbers, top minus bottom, or if you switch them to U's, then you can leave the U's in the problem right there. So on a U to U problem, notice same level of difficulty, about the same amount of time. Sometimes on the trig problem, it is definitely nicer. Like if I had my trig was like cosine of pi x over 6, I don't really want to plug back in a cosine of pi x over 6. But, you know, so a lot of times this method over here where you switch your x to u's will be a little bit nicer, especially on a trig problem. But typically time-wise, difficulty-wise, doesn't make any difference on a U to U problem, which method you use right there. However, on an x to x problem, if you could stop right there and not have to get the one single fraction and the common denominator and doing the GCF, and you could just plug in right there, that technique is really, really nice to just use those numbers right there. Also on an AP test, sometimes they'll have on the multiple choice on the AP test, they'll say, what's the intermediate step? And they'll have this down there. And that one of their choices will have the correct numbers, like the 1 and the 0, with those U's right there. So we won't see it like that often, but they could ask us to do that method with the U to U's and switching your X's to U's, or we have to kind of know that process right there. So like I said, XDX, not something we're going to use all the time, but it is something that it does pop up frequently enough where we need to know it. And I typically will only use, I never use an XDX on the trig. You already know how to do all the trig integrals there, so that's nice. But I typically only use it if I have a radical in the problem, and it's not like a normal integral where I could do a monomial that over that problem, you know, so, but it has radicals in the problem. It looks like it could be a U to U, but if I let the U go to the inside, the DU isn't matching up, so that's when I go to the next DX, and I let the U go the whole radical part, and then follow those steps there. That's the only examples I'm going to show you there, and then just try the homework there, and then we'll see what we run into with that stuff. There's some of them get a little bit messy there, but you know that all those messy problems just strengthen our algebra skills, sharpen up our skills where we're not making those little mistakes that we sometimes make there. So practice that as much as possible. Thank you.